So folks, Alex here. So today, for no particular reason, I decided to play a little bit with process tracing on Linux, right? And the aim for today will be to kind of understand what the strace utility does, and maybe like re-implement like some small part of it in Rust, right? Of course, there is a lot of work been put into a strace in order to make it like nice and actually useful and all that. We're not gonna do that. So the aim will be to just figure out what it does and maybe like try to poke the same strings from Rust, right? So what is strace? So strace is a kind of userland utility, right? That somehow can attach to an external process, right? And read its like and basically like subscribe to the stream of that external process's system calls, right? So the way it looks usually something like this. So imagine you have some kind of external process, right? So let's get the console PID, right? So sudo strace -p with this, right? And watch closely what will happen here as I type stuff here, right? So j, and each time I type, you can see that a lot of, a bunch of new lines appear in that log, right? And those lines are basically our syscalls. So syscalls that been issued by that process. And syscalls are, kernel invocation from userland into the kernel, right? So here you, for example, can see that at some particular point, this process is trying to read from fd0 a buffer with a particular len, which is 1 here, and the contents of that buffer appeared to be j, right? Exactly what we entered. And also, in order to like draw it back to the user, right, to just show it back to the user, we actually need to write it somehow. So this is exactly what's happening here, right? So it appears that somehow, even though the strace is a normal, userland program, somehow it can, interact with any external process and kind of sniff out the, inner working, inner kind of behavior of that process, which is kind of interesting. So we'll see how it works in a minute. So in order to see how it works, right, we could have just strace the strace. Like, what the hell strace is doing? Let's see. Now when I type stuff here, you will see, like each time I type, you will see not the system calls that being invoked by the Python console here, but the ones that being invoked by the strace itself, right? And turns out that basically what it does, it invokes a couple of system calls, one of which is PTRACE and the other one is wait for, and basically it does it in a loop. So, like PTRACE, like wait, right? PTRACE, wait, and so on, right? So basically, it looks like we only need to know how to poke into these two system calls from Rust. And by the virtue of doing that, we could have implemented something similar to strace ourselves, right? And thankfully, there is a good manual on ptrace and actually for wait for, I guess, right? So let's see the ptrace. So ptrace system call provides means by which one process, the tracer, may observe and control the execution of another process called tracey and examine and change the trace's memory and registers. So not only it can like read the stream of syscalls that tracey produce, right? But it can also like modify the state of tracey, which is very important. And actually, like all the debuggers on Linux actually use ptrace to do that. Like GDB uses ptrace, right? So the actual signature of that ptrace. This is not exactly how ptrace, how ptrace is in Linux, right? This is like libc's kind of wrapper around it. but this is kind of close enough for us to understand how it works. So as a kind of first argument, it would accept the request argument, right? Whatever this is. And turns out that request is basically like a mode in which PTRACE operates, right? Then it takes the PID of the process, like process ID basically, right? And also like 2 additional arguments, 2 void pointers to address and data. And the semantics of these 2 will depend on the request that is actually being issued, right? So what kind of requests are available? So the first one, of course, will be attach, right? So we need to attach from our process to an external process by using this PID, which would make this external process a tracee, right? And by the virtue of attaching, the tracee will receive the 6-stop signal and basically like freeze in place, right? In order for us to kind of start modifying it, reading its state, all that kind of stuff. The other thing is, of course, syscall. So PTRACE syscall, right? So this is another request that is available for our disposal, right? And it basically like sets up a kind of listener for a new syscall, basically, right? So let's go ahead and try to implement something like that. Let's try to like utilize those syscalls from our Rust program, right? And of course, in order to be able to utilize syscalls, you will be needing, like any reasonable person would imagine that we would have used something like libc, right? And specifically because it actually has a PTRACE implementation, not implementation, but the wrapper rather, right? And for the wait syscall as well, right? So that's that. So as I said, any reasonable person would do that. So this is exactly why we're not gonna do that. I don't know why. I feel unreasonable today. So if we are not gonna be using this, how would one, poke into the kernel then? So the way you do this, you can do this like using inline assembly in Rust, right? But then you actually need to know the kind of low-level interface between the user land and the kernel land. So Linux syscall table is the one we need, right? So this is a searchable table. Let's see PTRACE, for example, right? So each syscall actually has its own number and a bunch of like arguments. And as you can probably tell, there is a structure to that, right? So every single one has some kind of structure to it, right? So the structure is actually called Linux syscall calling convention, I guess, right? So let's see. Yeah, so for AMD64, the machine I'm in, the userland convention is usually like this, right? And the kind of userland to kernel land calling convention is this. It's basically the same, except for RCX and R10, right? So in kernel land, that argument is supposed to go here. So basically, how it's supposed to work. So if you need to call the kernel, first you put the kernel number within the accumulator registry, and all other arguments go in that order in that registers, right? So for example, request, which is a long, goes here, PID goes here, and the other go here, right? And the same for wait for, right? So it's like exactly the same. PID and some other stuff go here. So let's go ahead and try implementing something like that, right? So since our implementation of strace will be as strace, so I'm willing to call it as strace. So strace. Okay, so code this. Okay. Yeah, yeah, so our Hello World project compiles. Oh, this is way too huge. All right, so let's maybe try to imagine the basic structure that we are looking for. I'll add clap. Drive, I guess I need. So struct options and like PID is i32, and let's say use clap parser and drive parser and capture long, right? So let options is options parse, and let's save function trace process, right? And pid this, and who knows how it's implemented, so something like this. I cannot type today, I don't know. So unsafe trace process pid. So this is basically like the overall structure that we are aiming for. But as I said, we don't really know how to call syscalls from Rust, right? So let's go ahead and try to implement the PTRACE and wait for syscalls, right? So let's see the man PTRACE. So we will be needing to provide this request, PID, address and data, and this is the mapping, right? And PTRACE. So this is the mapping. Okay, so const PTRACE syscall, like syscall number, right? And I believe it's 101, yes. And we will be needing wait for syscall number, which is 61, I think. Wait for, yeah, 61. Cool. So unsafe function ptrace syscall, right? So it will take the PID. It will also take ptrace. It will also take the request, which is ptrace requests. It would also take so address and data, which are void pointers, right? So address is a kind of mute pointer to void, let's call it, and data is the same mute pointer to void, basically. i32, and who knows how it's implemented. So ptrace request, struct ptrace request, and it's not struct, it's enum. And what kind of requests we have? So oops. Okay, attach. Yeah, ptrace attach and ptrace syscall. So attach syscall, right? And we need numbers for those. So ptrace attach -ri user source. So attach would be 16, and syscall would be 24, right? So ptrace syscall, and let's see. So let's result. Okay, and now we need to implement the. Okay, so now we need to implement what's inside. Okay, syscall in out, kind of like that, but not exactly. So in rocks we put the ptrace syscall number, right? Then RDI goes requests, right? Request as usize. Then RSI goes PID, Then RDX is the address and data RDX. So address, RDX, and R10 is data. R10 is data, and yes, laid out rocks. Think like that. Result. And this is basically std arch ISM, yeah. And of course, that whole thing is unsafe. I wonder why. Cool. And let's go ahead and do the same thing for the wait for. So unsafe function wait for syscall, which takes the PID I32, returns I32 as well. And let's see. Okay, so rocks wait for number, PID. Let's see. Wait for. So PID goes to RDI, and then it does this. Okay, RDI 000. Yeah, I'm satisfied with that. Cool. Cool. So basically our main loop will be something like this. So first we need to attach, right? So that will be PTRACE syscall, yeah, PTRACE syscall PID, and request will be PTRACE requests attach, right? And for address and data, we don't really use those. So std ptr null mute, right? Something like that. Oops. Cool. So we are attaching, and we need to wait for this PID, right? And then we are tracing syscalls. And we do it by invoking the PTRACE syscall with this syscall request, which is 24. And these are not used as well, as far as I remember. Let's see. Syscall. PTRACE syscall. Yeah, it's about to be executed. Specified data, the address argument ignored. And yeah, I think we can ignore it for now. So let's just tracing process and attach the process and waiting for syscall. Syscall detected. Okay, let's go ahead and just try out what we have so far, right? So cargo build, right? Python 3 import os get PID, right? So let's go ahead and take this sudo target debug and strace, right? PID with this. Okay, waiting for syscall, and as I type here, you can see that this log is start to populate. Cool, so it kind of works somewhat at least, right? So I'm willing to actually trace all the output syscalls here for demonstration purposes, right? So the write syscall. The write syscall number is 1, right? So let's go ahead and do this. So it's like write syscall number is 1, right? And in order to even know what kind of syscall is being invoked, we actually need something else. So Rust libc. So how it's been implemented in libc. I think it's like user something something rec struct, right? So basically what we can do, we can user rec struct. We can try to like populate that structure user extract, type C, ulong is U64 of course, and like regs, and I believe we need like wrapper C and derive debug and debug and clone and copy, something like that, right? So let's see. And in order to actually read out that structure from the process, I think we need something like regs, PTRACE get regs, right? So read the traces registers, address specified in an architecture dependent way, la la la. Yeah, so basically like we are reading the regs into that structure, and we need to provide that structure within the data argument, right? So first we need to know what number get regs, so number 12, regs 12, right? So now when we have a stopped process, ptrace syscall PID, so ptrace request regs, address will be sdt ptr null mute, right? And data, data is actually something like regs and sdt mem 0 and 0 watts, like regs, right? 0 zeros. Yeah, so mute regs as mute this as this. Okay, so technically now we know that we've detected syscall, and now hopefully we've read the state of the machine, or of the processor basically, before the syscall, right? So let's go ahead and print it out. So maybe, I don't know, syscall detects it, and maybe like regs are regs, right? And let's do maybe this. So cargo build and sudo, let's go ahead and attach, right? So each time I type now, I should be getting a new record here, right? So these are different, right? Which is cool. So the syscall number is actually located within the ROX original, right? Because as we know, in order to call the kernel, we first need to like put a number of that syscall into the accumulator registry, right? But then the actual syscall itself within the kernel will modify the accumulator. So we need to like we need to see what was the original value of that accumulator, right? So let's go ahead and do that. So if regs like ROX original is write syscall actually, right? Let's do this. So syscall detected, write detected. Okay, writing la la la. Yeah, let's maybe clean up some noise here. Waiting. Build and sudo. And I don't really want those. Detected. Okay, so now I can see that it's actually detecting only write syscalls. So the thing is that I think it actually detects it twice, and the reason for that is that for syscall tracing, what's available is like 2 hooks instead of 1, right? Which both are invoked by this PTRACE syscall thingy. And the first hook will be kind of when the syscall is entering, like before it's entering, and the other one is like when the syscall is exiting. So we actually need to like distinguish these two. Maybe like let mute is, I don't know, is entering syscall like false, right? And here is entering, yeah, so we're toggling it. And let's see, so if not is entering, we'll do that. Okay. So now I only get just a single notification on the write syscall, right? Not two notifications, which is good, which is what I want. So the goal here is now to be able to read out the contents of that write. So here, as you can see, we actually have a pointer to a buffer, right? Which is being filled by the write syscall. And we also have the size of that buffer in bytes here, right? Which means that technically I could have just read out a trace's memory within that boundary and see what IO actually does, right? So see the data that been written to a particular file, right? So in order to do that, I think I need something else. So pick. Okay, so PTRACE. I think this, right? Pick text and pick data. Read a word at the address of trace's memory, returning the word as the result of PTRACE call. So let's grab it. It's like big data. So big data is 2. Okay. Data is 2, right? Okay, so now when we are here, I can actually do this. So it will be like PTRACE syscall, but you know what? It's not even that. I know that the size of that thing is located in RDX, right? So what I could have done is rex RDX map and like shift, right? And here I could have actually done something interesting. So mute data, maybe. Let's see. So mute data, and we are pushing the PID, big data. Yeah, so the pointer to a buffer is located in RSI, which is correct. Shift, right? Okay, and then we can actually collect it into a string, hopefully. Let's buffer, right, as char. Okay. Buffer is this, and FD was, so FD actually located in RDI. Signed into RDI. Okay, so D, and I don't really need that, so it's like buffer, and FD, yeah, fine, whatever, RDI. Cool. So, to just recap, right? When we're detecting a write syscall here, we will be reading the trace's memory using the pointer to a buffer that is being used by the syscall itself, right? And as we know the size of that buffer, that should not be a problem, right? And that's correct, right? Cool. I mean, sure. So let's see how it works. Let's see. Let's do build, and let's connect to our Python process. Yeah, so now, oh, you know what? Actually, I want it a little bit different. I want it to be like buffer, but, you know, in debug mode. It's just easier to see in debug mode. So yeah, so now when I type stuff, I can see what's actually being printed out, right? So you can see, you know, individual letters here. You can see the error message, like traceback most recent call, blah, 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 which is being printed to the second FD, which is standard error, right? And if I did something like, I don't know, like print right? So hello world been printed to the FD1, right? So it looks good. And what about something like, I don't know, with how it works in Python? I don't even remember. Some file txt, write as f, right? F, write hello world from the file. So yeah, we've written a bunch of bytes to a file, right? And here, as you can see, the FD for that file was 3. So it's not 1, not 2, but 3. So it looks like we can actually like sniff the processes IO basically, right? Using this technique, which is kind of cool, I think. So again, as I said, I'm not going to like turn it into a kind of full-fledged strace implementation. I just wanted to poke into kind of the you know, innards of strace, basically into PTRACE. So I think we've succeeded with that, and that's that. I'm pretty happy with what I have, and if you have any questions, post those into comments, and I guess I'll see you on the next time. See you, folks.